All right. Okay. That is. All right. Real analysis is about, well, it's the real is referring to the real numbers. And the analysis is referring to more or less calculus. And when I say calculus-ish, that means functions and continuity and sequences and limits and all of the bits and pieces that went together to make calculus on a secure, pure maths, rigorous footing after calculus had already existed for a couple of 100 years. Okay, so real analysis sort of became a thing in the 1930s and 50s. And a lot of the approaches that we have about it came together after the First World War and has continued to grow after that, but that's where it is. Okay, it's a way of being absolutely certain mathematically in a pure math sense about all of the things that make calculus work. That's what it's for. Okay. So, all right. I'm just going to look at my notes and make a decision of what I'm going to talk about first. All right. The first thing I want to talk about is some useful ways of thinking about functions that will make it easier to make sense of some of the things that are going on in real analysis. Okay. So in a pure math sense, a function is, a function is a rule which assigns to every number in a domain, or not necessarily a number, but it will all be numbers in real analysis, to every number in a domain, a number in a codomain. And so this is what a function is. It has three pieces. It has a domain, and it has a codomain, and there is a rule which takes things here and spits things out here. Well, that's one way of thinking about what it does. So there are many ways of matching up things in one set, and these are both sets. And this would be an element, which is usually a number. So there are many ways of matching up things here with things here, and not all of them are functions, but most of the things we think about are functions in the sense of there being some sort of formula that takes an input and produces an output. So this is already a model of what a function is. All right. Cool. It would be useful if someone asked a question at this point. If you're having trouble, well, yep. If you're having trouble thinking of a question of your own, imagine a question that someone might ask. Yep. Are there any requirements? Sorry? Yep. Okay, are there any requirements for the rule? And there is. To be a function, the rule must have a requirement is that every element here produces only one element here. And not just only one, exactly one. So there are lots of rules that connect. There are lots of rules that connect two sets together, which for elements here, they have multiple things they're connected to over here. And that is not a function. A function, each element here produces exactly one thing here and always produces the same answer every time. Over in statistics, we have random things that produce different answers each time. They don't count as functions in this sense either. So it always has to produce the same answer. So you are familiar with lots of different ways of thinking about functions. Has anyone here done multivariable and complex calculus? Yeah. That's okay. Oh. All right, let me just go back. I have a question there. Is the codomain exactly the same size as the domain? No, the codomain could be anything at all. And I will give some examples just so that you're aware. But the codomain could be smaller. It could be bigger than the domain. It doesn't matter. It's a selection of things that you think are things you're interested in discussing as possibilities of coming out of the function. They don't actually have to all be possible as things coming out of the function. Yeah, does that answer the question, Abby? Okay.
David, I have a question.
Yeah.
Here you use codomain rather than range.
Ah, yes, that is an important question. I did not use the word range because range is a different thing than codomain. The range is the selection of all things that actually do get produced by the function, whereas the codomain is just the kind of things that might be produced. So you have seen things that do that in Maths 1B and in multivariable calculus, where you have a function like this, for example. So this function has as its domain R3, and its codomain, you could say, you get to choose what you call the codomain. The codomain is things that are in R2 because they have two coordinates. But the range is only things that have 0 as their second coordinate. And so the range is not the same as the codomain. Right. So the codomain is much more commonly, the range is more commonly smaller than the codomain. Yeah. Does that answer your question, Grace?
Thank you. Yeah.
Okay. Now, you're not going to be considering functions like this in real analysis, because real analysis is not about multivariable functions. Well, sometimes they happen, but it's not about that. They're about functions where the domain is the real numbers and where the codomain is the real numbers in general, but possibly smaller. But there are going to be ones where the domain is something else. And there's going to be ones where it's not just the real numbers, but it's always something smaller than the real numbers. We're not going to talk about the complex numbers very much in this course, as far as I'm aware. Okay. They will be mentioned a couple of times. So all right, here we go. Here's my real numbers. And when I think of a function, I can think of a function in lots of different ways. So you're used to having functions where it says f of x equals, and then you have a formula. You're used to having functions where the rule is decided like that. But it doesn't have to be a formula. It just has to be a consistent rule which assigns to every x that you think of something that it goes with. So it might not be a formula, it might be just a description. And that description can be as convoluted as you like. It just has to produce consistently and unambiguously a thing. Every time you choose an x, there has to be a thing that goes with it, that is the result of the function. Yep. Okay. And what happens is that every number in the domain, because it's going to always be numbers in this course, every number in the domain has a function value to go with it. So you could imagine something that produces this. Now I'm going to put 10 there, and this produces 12, and this produces 14, and this produces 16, and then in this spot here, that's 11, and so on. And every number has an outcome attached to it. That's one way of thinking about what a function is, that every input number has a number attached to it. And this is how I used to think of functions in multivariable calculus, that, you know, in space, there's every point has a number attached to it, which is like its temperature or something. This is one way of thinking about it. And when you move along this line, this number changes to different numbers when you're in different spots. I call this the advent calendar representation of a function. It works the way an advent calendar for counting down to Christmas works, and every door has, you open it and there's chocolate behind it. Every number, you open the door there and there's a value behind it. Okay, so that is one way of thinking about what a function does. And it's very traditional since Descartes to interpret all of these numbers as heights and depths and draw a graph. So this is the way of seeing function that you've been most familiar with, where you interpret all of these numbers as heights, and you draw a dot at the appropriate height, and you get a graph. And that's the traditional way of drawing a function, but it's not the only way of thinking about what a function is. And it is sometimes useful to not think about this graph and just think about the real numbers and which number is attached to each one. Okay, I have another way of thinking about functions, and it is maybe not that way, sorry. So I have numbers here, and they have outputs here. So I could say that 0 is connected to 10, 1 is connected to 12, 2 is connected to 14, 3 is connected to whatever, and you can have this sort of diagram, where you can say these are the inputs, and these are the outputs, and this is what each one is connected to. That's this diagram, but with the real numbers. And even better, it's often useful to think of it as not with the arrows attached here, but just moving a number here and seeing what the matching number moves at the same time. Like that. So here's my X and this is my matching Y, and seeing how that moves. I'm just going to switch over to my computer. This is Desmos, or Desmos as the Americans pronounce it. And I could draw like a couple of lines like this. And I can draw a moving point on the x-axis. And I can make a function like and draw another point here. You don't necessarily need to know how to do this, but whoa, let's turn that off. As I move this one, the matching other point also moves. That's the picture I'm thinking of. So here when x is 0, y is 10, when x is 1, y is 12, and so on. And the further this green dot goes, the further the other one goes too. But on my page, I drew them downwards. Crap, that's silly of me, wasn't it? On my page, I drew the top one as the input and the bottom one as the output. And so that's that there, that as I move this point, the other point also moves. And if I zoom out a bit and see that this moves at a steady pace, the other one is going faster than this one is. I can do a quadratic, and thank you. That was what I was about to do. So with this one, as I move the x, the y moves like this. Go this way, it moves up, and then it slows down, and then it turns around again. And look at this. As I move this way, back here, it's changing its speed, even though I'm moving this at a steady pace. And so that's a useful way of thinking about what functions are doing without looking at the graph and watching what the graph is doing. Yeah. In case you're wondering, the teaching terminology for this is called some people call it a dynograph, which is short for dynamic graph, in case you're wondering. These are all useful ways of thinking about what functions are doing. And the reason I tell you them now is that when your lecturers talk about this stuff, it may be useful to switch your perspective to a different way of thinking about functions in order to make sense of what's going on. Functions are a general idea, which means that they have many ways of thinking about them, and the different metaphors of the way that you think about it will be useful in different settings, in the same way as fractions are a general idea and you can think about them in lots of different ways. So yeah, I don't have any good reasoning for you to why you would be considering to use it this way, other than this dynograph makes a lot of sense of the way derivatives work. That as you move this forwards, this moves at various different speeds, and those speeds are the derivative. Yeah, those who are in the Zoom, it's easier for me to look at the faces of people who are in the room, so I'm sorry if you feeling, I'm trying very hard to look at the screen as well. Okay, so that was just something that I wanted to point out. The only other thing to do is, in this one, I've organized the function by taking all the things in the domain and figuring out what number is attached to them. I could do it the other way. I could run through the codomain and write down which things produce them. That's the opposite way of thinking about this. It's much harder to think about it that way, but it is a useful way of imagining what functions do. So I can look at, I'm going to come back here. So when I look at this thing and I have x squared, I'm just going to draw it in this way first. This is connected to that. This is connected to that, and so is this. This is connected to 1, 2, 3. This, and so is this. This is connected to 1, 2, 3, 4, 5, 6. So this, and so is this, and so on. So every number. So this is one of these pictures, and it's a little harder to see what's going on in this one than it is in the other one, which is why the dynograph is so useful, because you can just see how, as you move it along, what happens to the result. But I can also think about this as going, well, here's the codomain. And I can say, well, this number comes from 0, and this number comes from 1 and -1, and this number comes from 2 and -2, and this number comes from √2 and -√2, and you can run through all the things in the codomain and write down what goes there. Yep. Yeah, that's okay. It's just this number just doesn't have any arrows going to it. So the question was, you would want the range, not the codomain. That's okay. This one just doesn't have anything that goes there, and that's okay. So you're right. All the ones that have arrows arriving there, they are the range. And so it would be much easier to draw the graph if you just didn't draw the ones that weren't produced. So that was a very good point, and it's worth pointing out. And it does naturally make you wonder what kinds, if want a name for functions where the codomain is the range. And there are names for that. They're alternatively called onto functions. And in this course, you learned the new and fancy word surjective, which were, as I've discovered, as words, invented not 10 years apart. Very interesting. And in French. So, yeah. So this is not necessarily a particularly useful way of thinking about what a function is, but in terms of picturing what a function is, but it is a way of thinking about it, to run through the codomain and say what arrives at this number. All right. Cool. What else have I got? Yep, cool. One more thing on functions is it is also very common. There are things in real analysis which don't look like functions to begin with, but can be thought of as functions afterwards. And the thing I want to point out is a sequence, a list of anything can be thought of as a function. A sequence has a first thing and a second thing and a third thing and a fourth thing. So for example, you might have the sequence of 1, a half, a quarter, an eighth, for example. And you can imagine this as a function that goes from the number 1 and produces the number 1 as the output, from the number 2 and produces a half as the output, from the number 3 and produces a quarter as the output, from the number 4 and produces an eighth as the output. The act of putting things in order in a list is automatically making a function that has as its domain the natural numbers. So a sequence is a function with domain the natural numbers. I believe in this course the natural numbers don't include 0. Could be wrong. But I'm pretty sure they don't, because we use them for this purpose. And there's a first term in the sequence. But I could be wrong. It doesn't really matter. Yeah. Yeah. So But anyway, it's worth checking with your lecturer whether the natural numbers include 0 in this course. It doesn't really matter for the purposes of what we're using it for, but sometimes we like to say that the first term in the sequence is actually the one that goes with 0 because the calculations are easier. And so what that means is a sequence can have all these ways of thinking about it that we did. So a function has a graph, and it has it has this advent calendar thing, and it has you know, this arrow thing, and it has this dynograph way of thinking about it. That is what we can do with sequences as well. So I can look at this, and it's much more usual to take the list of numbers Okay, so I'm just going to stop and answer this question. The sequence itself isn't all natural numbers. No, the sequence is these numbers. This is the sequence. And I'm not considering the first element as the number 1. I'm considering it as the function value of the number 1. So what I'm going to say is that this is f of 1, and this is f of 2, and this is f of 3, like that. Does that clarify things? Cool. All right. Of course, normally we don't write it that way. We normally write it as A1 and A2 and A3 and A4, something like that. Yeah. So generating functions, there's like a sequence of numbers, but they can be created by a function formula. Is that sort of what you're getting at? Yeah. Okay. So what I want to point out is that this thing here, here's 0, here's 1. This is A1. And then this is A2. And then this is A3. And this is A4. And we think of them as a moving point. So that's that dynograph thing that I'm talking about, that as the number moves forward, I see it as the natural number moves forward, like the first, second, third, fourth, fifth, the number that the sequence is moves along wherever it goes. And so in many ways, this is a new version because it doesn't actually have the original one. We don't have this thing moving along the natural numbers in our head. We just watch where this goes because it jumps from one to another, one step at a time. But you can also draw it as an ordinary graph. So A1 is 1, and A2 is a half, and A3 is a quarter, and A4 is an eighth, and so on. And you can draw it like that. So that's also a representation of this, this sequence. And it's useful to be able to switch between them when you need to. Yeah. I'm going to stop for a moment. Would anyone like to say something or ask a question at this point?
Which chapter from MCC are related with...
I cannot tell you which chapter from MCC this is related to. Sorry.
Which knowledge points?
Yeah. So,
which knowledge from MCC are related?
The only knowledge from MCC this is related to was the fact that different functions in MCC have different representations. They can be represented as a graph, or they can be represented as a move. Like when you do a curve, you can move from one place to another. It's not necessary to have studied MCC to do this course. And I can't tell you exactly which bits go with it. Yeah.
Thank you.
Okay. So that's functions. Cool. All right. It will still be important to be able to think of functions as graphs. Yep. Mm-hmm. Yep.
There's another type of function that generates functions, which not like the I derivative elements.
Mm-hmm.
Usually they're more useful in like probability.
Yep. So you got in probability and statistics, there were functions where there was a function, and its ith derivative, when you sub in 0, produced the elements of the sequence that you wanted. That's a perfectly good description of a function from the natural numbers to the real numbers. And the description is, take the natural number n, do the nth derivative of this other function and sub in 0, and that is the term of the sequence that I've got. And any description, however complicated, that's a perfectly good function. So that is a function that uses another function to figure out what this function is, which is fine. Yeah. Okay. Cool, cool, cool. Right. Okay. So I'm just going to switch completely to another thing at the moment and warn you something about the way real analysis works. And real analysis is a pure maths course, pretty much. Like it applies to applied math stuff, but it's a pure mathematics course. The point of it is to have all the rigorous proofs and stuff that make the calculus work. And so real analysis as a course is about proofs. The lecture videos will be full of proofs. The assignments they ask you to do will be full of proofs. Your workshops will be full of proofs. The whole course runs on proof. They're going to show you proofs and you're going to have to produce proofs. Warning you now. Proofs that you see other people make are going to have some of the intermediate steps filled in. They're not going to show you all of them. So I wrote it down because it's the most important thing I want to say about proofs, is that as you go through this course, when you see a proof, it will be very common for that proof to not have all the steps that are needed to make sense of the proof. And you're going to have to fill them in or talk to someone about it to fill them in. And this is the vibe of pure mathematics writing. And speaking. Your face-to-face lecturer, who this semester is Raymond Bozo, will expect you, will hope that you stop him and ask him, how did you decide to do that? And that is a really useful question to ask your lecturer at any moment. Possibly let him finish a sentence, or get to the end of a proof. A good question to ask at any point when your lecturer asks, do you have a question, is to pick a spot in the proof he's just showed you and say, how did you decide to do that? Or how did you get from this spot in the proof to this spot in the proof? Whenever your lecturer asks, are there any questions? Somebody should ask one of those two questions. That is my advice to you. It will make your workshops and tutorials better. And it will make your lecturer better. Not that he's not good, he's really good, but really important. And those are also the sorts of questions you can ask at the Maths Learning Centre. We won't always know exactly what the decision-making process is, but we can usually fill in a gap between one line and the next. So I just want to give you an example of that. This example is from Finna's textbook. I can't remember what the name of the textbook is, I'm sure it's, yeah, lectures in real analysis. Let me just show you. Literal cut and paste from like screenshot from the textbook, which is why it's a bit fuzzy. There is no rational number with square 2. And this is the proof. Suppose there are P and Q in N, with P divided by Q all squared being 2. Choose Q to be as small as possible. Now, Q is less than P, which is less than 2Q. So 0 is less than P minus Q, which is less than Q. And 2Q minus P is greater than 0. It is easily computed that this thing is equal to 2, contradicting the minimality of Q. I would like you to look at that for a moment and think of a question to ask about what happened there. Even if you don't have a question of your own, imagine a question that somebody might ask. What does the word minimality mean? It means okay, well, grammatically, it's a noun in this sentence, okay? And it means the state of being the minimum. Sorry? Yeah. But the state of being as small as possible. And it relates to this thing here being as small as possible. So the grammar tells me that it's a noun, but also the structure of the proof tells me, it says it contradicts this thing. And to contradict something, there has to be something that was assumed to be true earlier. And so we can go back and find what was assumed to be true. Well, we assumed this. We also choose it to be as small as possible. Well, that phrase, as small as possible, sounds like minimalness. And so that is what it means. Minimality means being as small as possible. So, okay. Good question. Analyzing maths is sometimes about the proof structure and sometimes about the grammar. When I read this, the first thing that occurred to me was, how did he come up with that? That was the first question that occurred to me. And so I'm just not going to do that. Just let me fill in some stuff. Okay, I'm just going to fill in some stuff so that when I put these notes online, it'll make sense. All right, so this first line, how did he get that? That's what I want to know. That feels like a lot of reasoning to produce that. So I'm going to come back here and think about what this means. I've got that P on Q squared is 2. which would seem to me to say that P on Q squared is less than 4. And so therefore P on Q would be less than 2. And the reason I've chosen 4 is because it's a square number, so I can square root it. And therefore P is less than 2Q. Okay, cool. That's this bit of it. Oh, cool. And 1 is less than P on Q squared, because that's the next square number on the other side. And so 1 is less than P on Q, and therefore Q is less than P. And that's this side. Cool. Yeah. I could have said P on Q is equal to root 2, which is less than 2, which is between 1 and 2. That would have been a way of doing it. But I was trying not to assume that the number root 2 existed. Yeah. Yeah, or that I knew what root 2 was. Knew that it was between 1 and 2. But this at least gives me that information. So what I can see is that there was no working in this proof in the lecture notes that told you how to get from here to here. We had to add 6 lines of working in order for us to understand that. This is going to be a thing. Now, Ray Bozo, your course coordinator this semester, is going to be more careful than the textbook is. Is going to fill in some of that stuff, but you may have to spend some work filling it in or ask him how it happened. Yep. So the question is, in assignments, will you be expected to write these 6 lines? I don't know. That is a question to ask your lecturer, because he'll be marking the assignments. But what I will say is that your assignments are not just for your lecturer. They're for you. And if you write an assignment and then you look back at that assignment in 3 months' time and you can't figure out how you did it, then you haven't written your assignment very well for future you. So if you need this to make sense of what's going on here, then you write it in your assignment. Your lecturer will start to teach you things that you're allowed to say and just skip. This is not one of those things. But there will be other things where there are theorems which allow you to say, you don't have to do all this intermediate reasoning, you're allowed to skip straight from here to here. But it is a really important question to ask along the way, because this course is about proof, and part of it, as you say, is about what's acceptable. Abby, you asked, how did I choose 4? I chose this number because it's a square number, which means I would be able to do the square root of both parts when I went from here, this line to this line. Thank you for listening to what I said. That how did you get from one line to the next, or how did you make a decision of what to do, is a good question to ask. I'm proud of you for listening carefully to what I said and putting it into practice today. That's okay. I'm not going to go there right now. Okay, cool. So just let you know, it's a thing. And it's totally okay to bring things to the Maths Learning Centre and go, there is no working between this statement and this statement. How did they get there? And we can help you figure it out. We won't already know to begin with. We'll muddle it through, and we'll hopefully get you to do it more than us. But just so you know, that's a thing you can ask. Also a thing you can ask your lecturer when he does his help time as well. So, all right. I am upset that this lecturer wrote, not lecturer, yeah, he is, but that professor, is he Professor Finner? That Professor Larison wrote, it is easily computed that. It is a thing that you will see in proofs. Yeah, cool. And we for the Maths Learning Centre, we try not to say that things are easy, because my big question is, how the hell did you choose that this is the thing that you should calculate? And that was something that I would like to ask Finna. Yes. But I think it comes from, I can see the 2q minus p here. I can see it here. And I can see the p minus q here. So I'm thinking that part of those are coming from there. Yeah, but I'm not 100% sure what's going on. But I'm going to skip from there. We can come back to it later if we want to, but I'm going to move forward and talk about some other stuff. One of the things I want to talk about is inequality reasoning. So inequality is a thing that's like an equation, but instead of being an equal sign, it's going to be a less than or greater than or less than or equal to, greater than or equal to. That's what an inequality is. And most people who have done high school mathematics, and all of you have, so well done, are used to equation reasoning. But inequality reasoning can be a little different. And so I just wanted to show you some acceptable ways of writing about inequality reasoning. All right, show that for n in end and n greater than or equal to 1, just in case n includes 0. The 2n plus 1 all squared is greater than 8n. So I'm going to show this without using mathematical induction, which is a thing that's going to turn up in the course as well. But I'm not going to use induction. I'm going to use direct inequality reasoning. So here we go. Two n plus 1 squared. It occurs to me that the only way if you can't think of anything to do, expanding it out is not the worst plan. So that's what I'm going to do. So this would be 2n squared plus 2 times 2n plus 1. You don't have to show this line, but I just wanted to be explicit about it. And so that would be 4n squared plus 4n plus 1. So at the moment, I haven't written an inequality sign yet. These are equal signs because these things really are equal. Okay, and I would like to get to being more than 8n. I do have a 4n here, which is half as much as I need. I got a 4n squared. If that n squared was an n, that'd be great. Now, I know that if n is greater than or equal to 1, then n squared is bigger than n. And so this is going to be greater than or equal to 4n. So since n squared is greater than or equal to n, 4n squared is greater than or equal to 4n. Yep. So when I write this greater than or equal to, it directly refers to this thing just here. No, don't need anything here. If there's nothing here, then the reader assumes it's the thing above that you're referring to. That was an extremely important grammar point. Well done. Thanks for bringing it up. There are other ways to do this, but I just want to point out that this is a reasoning that will sometimes be used, so I want you to see it in action. And this is 8n. And so here we go. This thing is equal to 8n plus 1. So this equals is not referring to all of these things. It's referring to just the one above it. And this is supposed to be, I'm aiming for greater than. Oh, well, 8n plus 1 is greater than n, greater than 8n. So this number is equal to this number, which is equal to this number, which is greater than or equal to this number, which is equal to this number, which is greater than this number. And so therefore, the thing at the top must be greater than the thing at the bottom. No, you cannot. So I'm just going to say that aloud so that it appears on the recording and the people who are online can hear it. You can't say that this is equal to this because there's a greater than or equal to in the middle. But you can say this is greater than or equal to this. So I've just been given an alternative proof. Yeah, that's fun. Can I just... So this was Grace just checking what we've got here. This is an alternative. So we got to this point, and then we're here, and this is greater than or equal to 4n times 2 plus 1, since n is greater than or equal to 1. Just to be absolutely clear, like that. And so therefore this is 8n plus 1, which is greater than 8n. That's an alternative version of the proof. So any of these things I can conclude is greater than 8n, but only the things that are connected by equals continuously are equal to each other. Just pointing out that it's a thing. You're allowed to use reasoning like this. Sometimes your lecturer will use it. Sometimes they won't. Sometimes they'll use other reasoning. But it is a very common thing to make a move like this and declare that this thing is greater than this thing. So inequality reasoning is, how did I just set n to be equal to 1, like at this stage just here? Is that what you're asking? Yep, I did it because this thing here isn't an equal sign. It's a greater than or equal to sign. So if I had replaced n with 1 just there, that would, and left it an equal sign, that would be wrong, because it's totally, you've completely noticed that that is not the truth. But a greater than or equal to, that's fine. You just got to be a bit careful, because it's if there's a minus here, then it will work differently than that. So just be a bit careful. Yeah. Yep. Yep. So David is saying that at some point in the proof, I was declared that n was greater than or equal to 1 at the beginning, which possibly was declared by the fact that it was in an n, depending on what n is. And other proofs that are similar to this, I have to use this statement somewhere in order to get my inequality to happen. And if you don't, then there would be some other magic. Yeah. So, but my point was to talk about this reasoning, which is cool. But that's what the n is greater than or equal to 1 is what provided my inequality to appear for the first time. Yeah. Okay. Cool. I'm really glad I talked about that. That makes me happy. I like inequality reasoning. It's one of my favorite things. But I say that often, that I think is one of my favorite things. So, yeah, you're asking, how would you know what to do in the middle here? Yep, in general, there is no particular general rule. But what I did at this point was compare what I had with what I was aiming for and going, well, how can I make this as close to that as possible? And I was thinking that if that was an n, it would be 8n. That was just a thought that occurred to me. And a different thought might have occurred to you, which was this, that I'd prefer this to be 2 lots of 4n, or maybe I can do it this way. And okay, some other advice. It is such a cop-out to say, just give it a go, right? Or, oh, you'll learn through experience. What you need to do is whenever anyone uses this, whether your lecturer in the videos or in the workshops or one of your other students, to try to notice the thing that they did. So you can include it in your list of possible things to try. That's a really useful thing to do. Every time it happens, stop and notice what happened and how useful was it? And especially the ones that didn't work out, go, what was it there that didn't get me anywhere? And what was it here that got me somewhere closer? Because you can't just learn from experience. You have to learn from reflecting on your experience. So whenever anyone says to you, as a lecturer says to you, oh, you just learn by experience, you say, that's a cop-out. What do you mean? If you want to be rude. But if you want to be gracious, you say, I'm going to mentally add, I learned not from experience, but from reflecting on my experience. Yeah. So you can, every time someone does working, it is a chance for you to learn something about, even if it's not the thing that they're teaching you, it could be the thing before the thing they're teaching you, which is about solving equations and stuff. Okay. Right. Cool. Right. How am I going? Got about half an hour before I want to stop. I have 2 things to talk about. So the first thing is about the absolute value function. The absolute value or modulus function is going to be used a lot in real analysis. And so you need to understand all the ways of thinking about it, but in particular, one specific way of thinking about it, which is going to be the most useful one for real analysis. Okay. So, and I'm going to just lead with that one. So the absolute value of x is how far x is from 0. It is a literal distance on the number line. And even more importantly, the absolute value of x minus a is how far x is from a. I'm going to talk about that for a second. Like, you know, distance from a to x. Okay. This is the truth that I want you to hold on to. Now, the absolute value of x is also, if it's got a minus sign, then remove it. Right? But it's really important to be able to think of this one in particular as the distance between things. So here we go. Let me show you something. I'm just going to build some things up, one step at a time. (15 minus 13) is 2, right? This is the number 2. And I know this because when I start at 13 and then I go, so 13, 14, 15, it's 2 to get from 13 to 15. So this is literally the journey from 13 to 15 is +2. Whereas if I did 13 minus 15, that would be -2, and that is the journey from 15 to 13. So, yep. Yep, it could be also from X to A, but yes, you're right. It can go one way or the other, but I'm making a point. I'm making a point here is that X minus A, crap. I'm gonna have to sharpen my pencil, sorry. X minus A is the journey from A to X, and it is definitely the journey from A to X. That's what subtraction is. It's one of the things that subtraction is. The journey from one place to another, where this is the end and this is the beginning. And so when I go back here and I'm just going to add an extra thing to this, it's not just how far X is from 0, it's how long the journey from 0 to X is. Like it's the size of the number X. Basically, that's the other thing the absolute value is. And so when I do this, the absolute value of X minus A, that is the size of the journey from A to X. All right, just wanted to point it out, that this is a thing. So last thing is, whether you're going, and you're completely right, whether I'm going from 13 to 15, or whether I'm going from 15 to 13, the length of that journey is 2 either way. And so that's the thing. Doesn't matter which way around these numbers are, the answer is going to come out the same. Okay. So I have a question for you. Actually, I'm just going to do 10 and 20 just to... Let me show you what this function looks like. This is what the absolute value of X minus 10 plus the absolute value of X minus 20 looks like. Could someone please say something they notice about this function's graph? Okay, so I've had our person in the room, sorry, don't know your name. Sorry? R1, say that it's constant from 10 to 20. Why is it constant from 10 to 20? It's okay not to know, because I'm going to tell you anyway. It is also symmetric about 15. All right, I'm going to go back to my camera. So this is the distance between x and 10 plus the distance between x and 20 . So if x is between 10 and 20, then the distance between x and 10 is this distance, and the distance between x and 20 is this distance, and so the total of those two distances will be 10, because that's how far it is from 10 to 20. Now, what it's doing on the outside is, you know, a whole other thing, but I just wanted to point out to you that I think this is cool. That because the absolute value of x minus something is the distance between somewhere and somewhere else, I can do this reasoning and get an answer and say, well, it's the same everywhere. Now, of course, if I'm over here, it'll be this distance plus this distance. And so actually, let's just look at this. So if x is over here instead, the distance from x to 10 and the distance from x to 20, it's going to be 10 plus 2 lots of the distance between x and 20. It's going to be this distance and that distance again and a 10. Which is just cool. I don't even need the absolute value here, because if x is more than 20, then x minus 20 is going to be a positive number. So there you go. I can use this distance reasoning to think about, to use absolute values to talk about distances. Yeah. Cool. Would anyone like to ask or add anything at this point?
It looks like proof is just we play with the concept of, as just you mentioned, that the concept of absolute value, that is interesting thinking and it's cool, as you said.
Yeah, and so the concept of absolute value, being able to think of it as this distance, makes it possible for us to do new kinds of reasoning. Yeah. Okay, now this argument will not come up very often in real analysis, this particular one right here. But this idea of it being a distance between things will be really important in real analysis, because real analysis is about the things that make calculus work, and calculus is about very small changes in things. And so we're interested in things being close together, which means we're interested in the distance between them being small. And so there will be things about absolute values like this. We're interested in how far apart things are. When you think about functions being continuous, you need it to, when you move a small distance, you need the output to move a small distance as well. So we're going to be talking about distances between things a lot in real analysis. Yep. Correct. So think of a real number as a 1D vector and the absolute value is the size of x. Yes. And that means that that's what I was getting at here. The number 5 minus 13 is the vector that goes from 13 to 5. And so that's a useful way of thinking about it sometimes. Okay. In the textbook, I just want to point this out. In the textbook, the definition of the absolute value is this, which I had never seen before until I read the textbook. The absolute value is the maximum of x and minus x. And so if you take your number and you figure out both x and minus x, then whichever of them is bigger, like greater, it's the positive one. And so that's going to be the absolute value, which I thought, I just laughed out loud when I saw it, because I went, oh, well, it's true, I suppose. It's kind of fun. And so I really like it, because when I draw the graph of x and minus x, and I take the maximum, which is the one at the top, then I get that. So it's just like, it's just so cute. So anyway, I'm pretty sure there are some arguments in the textbook that use this fact. Yeah. Cool. Anyway, that just laughed out loud. Yes. So I'm going to add that in. We're going to join together our absolute values and our inequalities. I know that the absolute value of a number is greater than or equal to the number itself. If x is positive, the absolute value is the same as the number. And if x is negative, then the absolute value is going to be positive, which is going to be more than the negative number. Which is cool. And it doesn't matter, you can write it around the other way if you need to. Yep. This is the way that it makes it's easier for me to think about it this way. That's also true. And the other absolute value inequality that is the bread and butter of real analysis is called the triangle inequality. Is it this one? What other one's that? Ah, yeah. This is called the triangle inequality. It is a reference, which is a reference to this idea, but with vectors. So when you think of vectors and you have the vector A and then the vector B, and then this vector is the vector A plus B, then the third side of a triangle has to be shorter than the other two sides, because the journey is shorter, because it's the straight journey as opposed to a kinked journey. And so we're thinking of them as vectors, but we're doing it as vectors on a line, exactly as you said. So, yeah. So when one of them is positive and one of them is negative, A and B, and this is A plus B. The length of A plus B is shorter than the length of A plus the length of B. If they're both positive, then the length of A plus B is the same as the length of A plus the length of B. So, yeah. But it's called the triangle inequality because it's true for vectors as well, and vectors in space. Yeah. Yeah. So that would have turned up in algebra 2 when you were doing norms of vector spaces, if you did algebra 2. Yeah. Yeah. So that's pretty much the main one. There is another one, I'm sure. Yeah. So yeah, there's all other ones as well. And this is a way of getting to that. And look at this. If A was positive, then you'd be able to do some stuff as well. So yeah. And if you had A plus B is going to be less than or equal to, no, it's not going to work. It's okay. One of the annoying things in real analysis is when your inequalities point the opposite way to each other and you can't fix them. You try and join two inequalities together. Yeah. Oh, back under inequality reasoning. just want to add something back under inequality reasoning, which is that, pardon me, because you can add two inequalities together if they're the same kind of inequality and they're pointing in the same direction. So I can add these two and add these two, and it's still a true inequality. The reason why you can do that, the long version, is that I'm allowed to add the same thing to both parts of an inequality, and it's still true. But then this is less than or equal to 3 plus 7, which is 10. So that's the long version, but you're allowed to just do it straight up. Yeah, well, if one of them's just a less than, you'll get a less than here. Yeah. So be very careful with them and test it with some actual numbers just to make sure it works when you do it. Because so anytime you're unfamiliar with it, you can things can go a bit weird. Yeah. Okay. All right. So there will be a lecture video on this. It will be there, but I just wanted to set you up that it's coming. And it will be some of your first proofs, taking the triangle inequality and proving other versions of it. Yeah. Last thing, just before I finish off, and it's just some set notation stuff just to make sure that we're all on the same page. Okay. I'm going to do set notation, but I'm not going to draw any Venn diagrams because I want to do all your set operations on the real line, because that's what you're going to be doing. So this is set builder notation, they call it, with the curly brackets. So inside here, you have to have a description of how to tell if something's in the set. And you can either have a list, or it's much more common to have something like this. It's just an example. So this is the set of, that's what these bits tell you. The set of numbers X and the real numbers, I know they're numbers because they're in the real numbers, such that so this symbol here is such that, and I should point out that some lecturers, instead of using a vertical bar, use a colon instead. Especially if there's an absolute value here, because then it can be confusing. Such that right. Or if you like, the distance between X and 3 is less than or equal to 2. So this is called set builder notation. And there are two ways to use set builder notation. You can either have the kind of thing that you're looking for on the left and a condition to satisfy on the right. Or So this one is you could also have something like this. Instead. So this is the set of the set of numbers n squared minus 3 on n such that n is in the natural numbers. This one is different. This is also set builder notation. Whoa, sorry. I bumped something. Here it comes. Okay. And this isn't, back here, it wasn't just things, it was types of thing, right? Whereas this one was a construction and technical details, right? So this notation n is in n, it's in both of them, right? This one had an x in R, this one has an n in n. It's in both, but they're on opposite sides and they're doing different roles. This one, I'm using all of these and doing this calculation and producing all of the answers for this, and that is what my set is. Whereas in this one, I'm getting all of these and I'm checking whether this is true or not. And for some x's, it's going to be true, and for some x's, it's not going to be true. And the ones where it's true, they're the ones in the set. If I did this, no. So I'm just going to do some grammar here. This is meaningless because the thing that starts this sentence has to be an object, and this is a statement about an object, not an object itself. So in both of so I mean, this is a statement about an object, but it's actually, this is an X which is in our, oh wow, how fascinating. It's just not said that way. It would actually be, oh, that's so cool and frustrating. Great question. That is, you have just pointed out something that I hadn't noticed about how maths is still language and therefore can be ambiguous and esoteric at times. We don't write this ever. We could write this, and that would be a set, but it wouldn't be the same set. Fascinating. Okay. Nope, you don't. And you, like, we don't know what n is, and we have to wait for here to figure out what n is. And you're right. That is just, but the thing is, maths is a language, and there will always be things that are weird about the way language is written. And so this is the only verb we're allowed in this side is an in, and a member of symbol. Everything else has to be a noun phrase, just a single object that has been made out of other stuff. So we either have stuff made out of things and then the things it's made of, or we have kind of object, and it's usually just a single letter. In fact, it almost always will be single letter, and then the condition to decide if if we're allowed to use it or not. Yeah. Okay. Both of these will happen in this course. I hope my battery lasts a couple of minutes. If it doesn't, I'll just stop and goodbye everyone if my battery runs out. Sorry. Okay. So notice this set, I can draw this set. I can draw both of these sets. This set is going to be a collection of dots, one for each. This set is going to be all the numbers whose distance from 3 is less than or equal to 2. So this set, here's my number line. Here is the number 3, and the distance away from 3 is less than or equal to 2. That's what this says. All my x's, the distance from 3 is less than or equal to 2. And so that is everything from 1 to 5. Like that. This is that set. Yes. So yeah, you could write x such that x is in R, and if you wanted, but the shorthand is to write this like that. Yeah. Good thinking. Okay. So just pointing out that this set is this set here. There is likely to be a notation for this in this course. I don't know what it is. When I did the course, it was called the ball with center 3 of radius 2. But I don't know if that's still true in this course. Yeah. But I can write it in another way. This is the closed interval from 1 to 5. And so interval notation is going to be a thing as well. So we're going to have things like the interval from 2 to 3, and it's going to be open at one end. Like that. All the numbers where x is 2 or above, up to but not including 3. And because these are the real numbers, it could be anything up to 2.9999999, as many nines as you like, but not infinitely many. And basically, sorry, because then it is 3, yes. And so this is the set of x's in R such that 2 is less than or equal to x, which is less than 3. But this is shorter to write. And so all combinations of this are possible, and you can write things like, 3 infinity. There it goes. Okay, computer turned itself off, but I'm back now. This one would be everything from 3 upwards forever. That's what this is. So point out that in real analysis, you'd never put a square bracket next to an infinity, because the number infinity isn't a real number, or possibly even a number at all, but whatevs. This symbol is not a number in this context, and so it can't be in the set, and so you can't have a square bracket there. So just point it out. That's a grammar that we use. The one thing I really wanted to talk about was intersections and unions and stuff. So you can take sets that you already have and you can join them together or do operations on the sets to produce new sets. And so there are 3 main operations on sets that appear in real analysis. There is, which is union. And the definition of A union B is the set of X. We're going to do it in the real numbers for the moment. This is just operations on sets of real numbers. Is a set of X's in R such that X is in A, or X is in B, or possibly both. And A intersection B is the intersection, which is the set of X's such that X is in A and X is in B simultaneously, like at the same time. It's in both of them. And A without B is the set of X's in. Now I could say it's the set of X's, but I'm going to do this. The set of X's in R such that X is in A, but X is not in B. Some mathematicians write this as A minus B. Freaks me out when people do that, because I like having special symbols for sets that are different to the symbols I use for numbers. But I just wanted to point this out, that in some places in the world they write it as A minus B with a literal minus sign. Oh, it totally makes sense. Yeah. Yep, it's called set minus in LaTeX. Yep, but still just freaks me out. I just like having different symbols for sets as I had than I have for numbers. Okay, and I read it aloud as A without B, because it makes sense to me. Yeah, I think your lecturer will use this symbol. Yeah, in this course. Sorry? Complement's just not a thing that normally turns up, right? It'll just be R without. Sorry? Well, I mean, the complement is like A, C, or A bar or something. And I don't think that's in this course. I could be wrong, but it's just R without A, like would be A bar usually. But A bar can, in some contexts, mean that you include the endpoints if they weren't included already. Like it could mean the closure of A. So like I just don't want to go there. I'm just going to run with this. And I just want to draw some pictures of what this looks like in the real numbers. So one thing I want to say is this word or and this word and are how people often talk about these things. But it's really important to know that those conjunctions are conjunctions here in the condition that decides whether you're in this set or not. When you draw the pictures, this will look like A and B glued together. So just point it out. And people should be familiar with this already. If they've come through the whole first year of a University of Adelaide maths degree, then you should be familiar with this. But I just wanted to point it out one more time, just in case. So just as an example, if I have the set I have these two sets. Just going to draw them below my number line. Here's 1, here's 2, here's 3. Oh, nope. Can I just change this to a 5? Yeah. Now I have used nice whole clean natural numbers here, but there's no reason why they can't be. I might as well, I'm allowed to put a half here if I want, and that's okay. And I will just for completeness' sake. So this is my set A. And this is my set B. A intersection B, oh sorry, A union B is what I get when I glue these two sets together. The decision of whether something is in A union B is that it's either in A or B or both. So as I run along these numbers and decide whether it's in this set or not, that number is not in A and it's not in B, so it's not in A union B. And when I get to here, all of these numbers end up being in A union B, and these ones too, because they're all in A, and these ones too, because they're all in B, and then I stop being in A union B. And so A union B will be all of this. I glue the two sets together. So in that context, it's A and B glued together. But the decision of whether a single number is in A union B is an OR decision. Sorry? Yeah. So they overlap, so I'm able to just glue them together. I will deal with ones that don't overlap in a minute. A intersection B will be all of the numbers that are in both A and B at the same time. So when I run along all my numbers, these numbers aren't in A, and so they can't be in A intersection B. These numbers are in A, but they're not in B, so they can't be in A intersection B. These numbers, they're in both. And these numbers are not in A, so they can't be in A intersection B. They're in B, but they're not in A. And so the numbers that are in both are these numbers here. And at the endpoints here, this number 4 is in B because it's included because of the square bracket, and it's also in A because it's between here and here. And so it is part of A intersection B. But this 5 isn't in A, so it's not in A intersection B. And A without B would be all the bits of A that aren't in B. So this bit's in A, it's not in B. This bit's in A, it's not in B. This bit's in A, it's not in B. This bit's in A, but is in B, so that's not allowed. And so I'm going to have that. And I removed the 4 because it was in B, and so it's not allowed to be in A without B. But B without A would be this bit. I didn't remove the 5 because it wasn't in A to remove, and so it's still there. Right, and so if you look at this, A intersection B and A without B and B without A together make up A union B. So those three sets together make up A union B. They're the three pieces of A union B. So I'm going to do another example. There we go. Just to make it hard for myself, that's not a B, that's the number 8. And so here we have -1, and 5 halves is 2.5, and here's 8, and here's 10, and A is this, and B is this. So A union B is A, because this one's in A, this one's in A, this one's in A, this one's in B, that they're, when I glue them together, I don't get anything new. Right. A intersection B is B, because if I'm in both A and B, well, all of B is in both A and B. And A without B is, well, this bit and this bit. And they don't overlap. Like, I'm going to have like that. This whole thing, both of those things is A without B. And so this is actually the set from -1 to 5 on to union from 8 to 10. And there's really no other way of writing this set. I have to keep this U here to say that I am imagining that both of these are part of the same set. And I need it there. And there's no way of doing what I did over here of joining them together and getting, you know, from 1/2 to 7 to make one big set. I have joined them together to make one big set, but it's made of 2 smaller pieces that don't overlap. And that's how I have to write them. And B without A is nothing. Because if I remove all the things that are in A, I've removed everything. Yeah. So it is okay for your set to be made this way, to just have 2 separate intervals that don't overlap. And this is the only way to write it. So.
Like those instances like come together. So what I mean by that is, you know how there's an overlap, right? If both sets contain like there would be number 2, they might think there are 2 2s.
Ah.
Like that's not actually.
So I'm just going to repeat that. When some people think about unions, they go, oh, well, this contains all the numbers from 1/2 to 5. This contains all the numbers from 4 to 7. So all the numbers from 4 to 5 are sort of in here twice. And that's not true. They're only in here once. Yeah? Yeah. Yeah, okay. That's a whole other thing. But yeah. But yeah, it's not like there's a 2 from here and another 2 from here. It's the same 2, and so it is only in here once. Yeah. And so this decision here it's why it's an or. We have to think of it when we do this sort of set things. So good point. You have to think of it as a decision about, is the number 2, which exists independently of these sets, is it in the final set? And the answer is yes. And it's not in there twice. It's just, I'm really sure it's in there. I'm twice as sure it's in there, but it's no more in there than it was before. Yeah. So yeah. And so you can join as many sets together as you want, and sometimes they come clean into something nice and sometimes they don't. So there's a nice thing where you can say, yeah, so you'll come up to various notations that'll come, but I just wanted to remind people that that's what those things are, just so that you do it. And intersections will happen sometimes. And as far as I can tell in this, it's really just a way of making sets so that you can ask questions about them, with nothing in particular other than that. Cool. All right. There will be plenty of things. One of the implications of doing this seminar is that you can ask us about, especially the things that are in this seminar as we go along. So as you go through the course, and you keep coming up with things to say, oh, David mentioned that in the Ready for Real Analysis seminar. That means I can definitely ask about it at the Maths Learning Centre. And I think that that's a useful thing to know, that you can definitely ask us about notation things. Sometimes it'll be, that's a thing that's only in real analysis and we'll just have to look it up. And if the staff are doing their job properly, then they should go, that might mean something different in real analysis that it does over in another course, and we should look it up. So feel free to say to them, are you sure it's definitely this? So that you can make them look it up in the notes. Yeah, I hope that was useful. And thank you for your input, and those online, thank you for your input. And good luck with real analysis. I hope to see you as we go.